On November 14th, 2023, a machine 15 billion miles from Earth opened its mouth to speak, and nothing came out that made any sense. Not silence. That would have been simpler. Silence, engineers can work with. What came back instead was noise, scrambled, repeating meaningless noise, arriving right on schedule every single day exactly when it was supposed to. The spacecraft was alive. Its heartbeat was steady, but whatever it was trying to tell us had turned into something no human being on the planet could read. For the first time in 46 years, NASA's most experienced deep space engineers sat in a room in Pasadena, or California, and admitted they did not know what their own spacecraft was saying. This is the story of what happened next, because Voyager 1 did not just come back from that silence. It came back carrying a discovery that scientists still cannot fully explain, and a countdown that is closing in on all of us faster than anyone expected. Let's go back to where this actually starts, because you need to understand what this machine is before you understand why its sudden silence sent a chill through one of the most seasoned engineering teams on Earth. Voyager 1 launched on September 5th, 1977. It was built to last 5 years, maybe 6, just long enough to fly past Jupiter and Saturn, snap some photographs, and quietly power down. Nobody expected it to still be running in the 1990s. Nobody expected it to still be running in 2010. And yet, here we are, decades past its expiration date. And Voyager 1 is not only alive, it is the single most distant human-made object in existence, farther from Earth than anything our species has ever built or sent anywhere. It runs on roughly 4 watts of power right now. For comparison, the bulb in your refrigerator uses more electricity than that. This aging, underpowered machine, built with less computing power than a modern calculator, has been quietly rewriting what we know about the edge of our solar system for over a decade. And in 2012, it did something no human object had ever done before. It crossed the heliopause, the outer boundary where the sun's influence finally gives way to true interstellar space, and it kept transmitting from the other side. We have had, since that moment, a live instrument sitting in the space between the stars. Nothing else humanity has ever built has been able to say that. So when I tell you that this machine suddenly stopped making sense in November of 2023, understand what that actually meant to the people who have spent their careers listening to it. This was not a glitch in some app. This was arguably the most important scientific narrator we have ever had, sitting 15 billion miles away, suddenly speaking in a language nobody could decode. Here's what actually happened, and this part is not exaggerated because it does not need to be. Voyager 1 has a system called the Flight Data Subsystem. Think of it as the part of the spacecraft responsible for packaging up everything it observes and everything about its own health, and formatting that information so it can be beamed home as a readable signal. In mid-November 2023, that system began transmitting a signal that was, in the words of the engineers who first saw it, a repeating pattern of ones and zeros that didn't match anything meaningful. It was as if the spacecraft had started speaking gibberish, on purpose, on a loop, day after day. The carrier signal itself, the basic radio tone that tells Earth, "I am still here, I'm still alive." That part came through clean. Voyager 1 wasn't dead. It was worse than dead, in a strange way. It was alive and trying to talk, and failing. Now here is where the real difficulty sets in, and it's a difficulty that has no equivalent anywhere else in engineering. Voyager 1 is so far away that a radio signal moving at the fastest possible speed in the entire universe, the speed of light itself, takes over 22 hours just to reach it. And then another 22 hours for any reply to come back. So if an engineer at the Jet Propulsion Laboratory wanted to test a single idea about what might be wrong, they had to write the command, send it out into the dark, and then wait nearly 2 full days, sometimes longer, just to find out if their guess was even close. Imagine debugging a problem where every single test costs you 2 days of waiting, or a single mistake could permanently end a mission. That has been running since before most of the engineers in that room were even born. That is what the Voyager team faced for 5 straight months. They worked through it the only way you can work through a problem like that. Patiently, methodically, piece by piece. Eventually, they traced the fault to something almost absurdly small for the scale of the crisis it caused. A single memory chip inside the flight data subsystem had degraded. Just one chip, likely worn down after nearly 5 decades of continuous exposure to cosmic radiation in the harshest environment any human-made object has ever operated in. That one small failure was corrupting roughly 3% of the memory responsible for organizing Voyager 1's data before transmission. 3%. That was enough to turn the most important scientific voice in the solar system into static. The fix, when they found it, was almost unbelievable in its own way. They couldn't repair the chip. It was gone, deadweight, unusable. So instead, they did something that sounds more like microsurgery than spacecraft engineering. They split the affected code into smaller pieces and relocated those pieces into other parts of the spacecraft's limited working memory, rewriting each section so it would still function correctly from its new home, then stitching the whole system back together so it would work as one. And they did every bit of that from a room on Earth, sending each instruction across 15 billion miles, waiting nearly 2 days for a response, adjusting, and sending the next instruction. It took months. In April of 2024, Voyager 1 spoke clearly again. Real data, real science, coming home in full sentences instead of static. And here's the part of the story that I think deserves more attention than it's gotten, because when Voyager 1 came back online, what it resumed sending was not routine. It picked back up in the middle of reporting something that scientists still cannot fully explain, a signal that had first been detected years earlier and has only gotten stranger the longer they've studied it. Starting back in 2017, long before the communication blackout, an instrument on Voyager 1 called the Plasma Wave Subsystem began picking up something in interstellar space that nobody had predicted. A faint, narrow, persistent hum. Not a one-time event, not a burst that could be written off as noise. A continuous signal that has now been tracked across a stretch of interstellar space more than 900 million miles wide. To put that in perspective, the distance between the Earth and the Sun is 93 million miles. This emission has been detected across a region 10 times that size, and it just keeps showing up year after year as Voyager 1 drifts deeper into the dark. For decades before Voyager 1 actually got out there, physicists built careful, peer-reviewed models describing what interstellar space should be like. Those models generally agreed on one thing: it should be quiet, thin, calm. A cold, sparse in-between space where not much happens, the kind of place you'd expect between the fireworks of actual star systems. Voyager 1 flew into that supposedly calm region and instead found something closer to a low, steady storm. Researchers publishing their findings in the peer-reviewed journal Nature Astronomy described interstellar space as turbulent, with structure at every scale. From distances you could measure in meters up to distances measured in millions of miles. In other words, the void between stars is not empty and it is not quiet. It has weather, it has texture. And until one aging spacecraft flew directly through it, we had absolutely no way of knowing that. Before this emission showed up, the way scientists studied interstellar plasma was more like taking a single photograph once in a while than watching a live broadcast. Occasionally, a massive eruption from the sun would send a shockwave rippling all the way out past the heliopause. And when that shockwave hit the interstellar medium, Voyager 1 would catch a brief, isolated spike in its instruments, a single data point in an otherwise dark and silent record. That was the best information we had for years, scattered snapshots separated by long stretches of nothing. What changed in 2017 is that Voyager 1 started picking up something continuous instead. Something closer to a running signal than a single flash, day after day, month after month, as the spacecraft physically moved through the plasma itself. For the first time, scientists weren't reconstructing interstellar space from rare, indirect clues. They were getting something close to a live reading, and that reading kept insisting the space out there had far more structure and motion than anyone had modeled. There's also a piece of this story that reaches back and touches home in a way most people don't expect, and it has to do with the boundary itself, the heliopause, the very edge Voyager 1 crossed back in 2012. Scientists had assumed for decades that when a spacecraft crossed that line, the transition would be smooth, almost gentle, the solar wind fading out gradually while the interstellar medium gradually took its place, the way a river slowly blends into the sea. That is not what the instruments recorded. Right at the boundary, particles were found moving at extraordinary speeds, colliding with enough energy to generate temperatures in the tens of thousands of degrees, in a region that was supposed to be cold and mostly empty. And when researchers examined the magnetic fields on either side of that boundary, expecting to find two completely separate systems, the sun's magnetic field on one side and the galaxy's on the other, they instead found evidence that the two were interacting, exchanging energy through a process called magnetic reconnection. That matters here on Earth because the heliopause isn't just a scientific curiosity. It functions as a shield, deflecting a significant portion of the high-energy cosmic radiation that constantly streams in from distant, long-dead stars. So, if the boundary protecting our solar system is more dynamic, more turbulent, and more tightly linked to the environment outside it than our models assumed, then the question of how stable that shield really is over long timescales becomes one we still don't have a confident answer to. Here's the part that scientists genuinely have not resolved. And I want to be honest with you about this instead of pretending there's a tidy answer, because the honest version is more interesting anyway. There are two competing explanations for what's actually causing this persistent plasma hum, and researchers studying the data have not been able to determine which one is correct. One possibility is that it's thermally excited plasma oscillations, essentially the natural vibration of charged particles interacting with their environment. That would be a real and meaningful discovery, but it would still fit inside our existing understanding of physics. The second possibility is something called quasi-thermal noise, a different mechanism entirely, one that would require us to meaningfully revise our models of what interstellar space actually is. Two very different explanations. One spacecraft, not enough information yet to know which one is true, and the instrument that could help settle it is running on a power supply that loses a little more electricity every single year. Because that's the other piece of the story that nobody can ignore. Voyager 1 is dying, slowly, on a fixed and calculable timeline. It's powered by 3 radioisotope thermoelectric generators, essentially containers of decaying plutonium that convert heat into electricity as the plutonium breaks down. At launch, in 1977, those generators produced about 470 watts of power. Today, they produce somewhere around 250 watts, and they lose roughly 4 watts every year. Engineers have known for a long time exactly where this is heading. Of the 10 scientific instruments Voyager 1 originally carried, 7 have already been switched off, one by one, in a carefully planned sequence designed to squeeze the maximum possible science out of a shrinking power budget. Each shutdown is permanent. There is no way to turn an instrument back on once its power has been reallocated elsewhere. Every choice the team makes now is a choice about which questions will simply never get answered. And yet, this is a mission that has made a habit of refusing to end on schedule. NASA engineers have spent the past couple of years experimenting with ways to redistribute power across Voyager 1's aging systems, looking for small pockets of electrical capacity that might still be recoverable from components running less efficiently than they should. It's delicate, uncertain work on a spacecraft with no manual override and no possibility of a repair mission, which is exactly why any changes have been tested first on Voyager 1's twin, Voyager 2, which has slightly more power to spare and sits somewhat closer to home. If those experiments prove safe, there's a real chance some of the instruments already switched off on Voyager 1 could, in a limited way, come back online. Nobody on the team is promising that. But given everything this spacecraft has already survived, nobody's ruling it out either. To understand how strange that recovery in 2024 really was, it helps to compare it to how we'd normally fix something this broken. If a critical component fails in a machine on Earth, you send someone to look at it, or at the very least, you get a live diagnostic reading back in milliseconds. Every ordinary rule of troubleshooting assumes you can react quickly, test an idea, and immediately see whether you were right. None of that applied here. The team effectively had to diagnose a stranger speaking gibberish through a phone line with a 2-day delay on every single word, with no way to physically inspect anything, and with the full knowledge that one wrong command sent across 15 billion miles could end a 46-year mission permanently, with absolutely no way to undo the mistake. That they solved it at all, using a spacecraft built with less processing power than the key fob for a modern car, is the kind of achievement that tends to get a few days of news coverage and then quietly disappears from public memory. It shouldn't. It's one of the more remarkable pieces of problem solving in the history of spaceflight, and it happened almost entirely out of public view, across a distance most of us can't really picture. And there is a date already locked into the calendar, one that has nothing to do with any of these uncertainties, one that is going to happen no matter what. On November 18th, 2026, Voyager 1 will cross a distance of exactly 1 light day from Earth. That means a radio signal, again moving at the fastest speed anything in this universe is capable of, will take a full 24 hours just to reach it. Send it a message on a Monday morning, and you won't know if it arrived until Tuesday morning. You won't hear back until Wednesday. No human-made object has ever been that far from home, not once in the entire history of our species. And Voyager 1 will cross that threshold while it is still alive. Still speaking, still sending pieces of a story we don't fully understand yet. Every hour that passes, it travels another 38,000 miles farther out. The power keeps dropping. The delay keeps growing, and sometime in the early 2030s, by every current projection, the output from those generators will finally fall below what's needed to keep even a single instrument running, and the last signal will begin its slow journey home. When it arrives, there will be nothing after it. Voyager 1. Itself won't stop, though. There's nothing out there to stop it. No friction, no atmosphere, nothing strong enough to pull it off course. It will simply keep moving in a straight line at 38,000 miles an hour, forever, carrying a golden record bolted to its side, engraved with greetings in 55 languages, the sound of rainfall, the sound of human laughter, a map showing exactly where in the galaxy it came from. So here's where I want to leave you with the question that actually matters, because it's bigger than one machine and one glitch. Right now, in 2026, the only functioning scientific instrument our species has ever placed in the space between stars is 49 years old. It was built using slide rules and technology that predates the personal computer. Its brief, terrifying silence in 2023 turned out to be a single failing chip, And even after everything, it came back and picked up exactly where it left off, still describing a region of space that our own models never predicted correctly. There's a real, unresolved scientific question sitting inside that plasma hum, one of two very different explanations, and we genuinely do not know which one is true. The instrument that could help us find out is running out of power, on a clock that nobody can pause, and there is no second Voyager 1 waiting to take its place. If a new mission designed for interstellar space were funded and launched today, it would not reach the heliopause for at least another 25 years, which means that whatever Voyager 1 is trying to tell us about that turbulent, uncharted region outside our solar system, we may only get to hear the beginning of the answer. The signal is still coming right now, stretched across 15 billion miles, arriving 22 hours late, carrying a mystery scientists still haven't cracked. And somewhere out past the reach of anything else we've ever built, a machine the size of a small car is still listening, still speaking on 4 watts of power for as long as it possibly can. If this is the kind of story you want more of, subscribe and turn on notifications, because we're going deeper into what's actually happening at the edge of known space next. And drop a comment telling me which explanation you think is right, the quiet physics answer, or the one that means we have to rewrite the textbooks, because I want to know what you think before the signal goes quiet for good.